All right, so remember those old right-hand rules where if we got current in the wire, we point our thumb in direction of the current, magnetic field wraps around. Meanwhile, for a solenoid, we put our fingers in direction of the current, and then our thumb will point to the North Pole. Well, good news. We've got another one. The bigger one, probably the more often used one. For this one, we have thumb pointing in the direction of the current, middle finger pointing in the direction of the force, and pointer finger in the direction of the magnetic field. What that looks like is you've got three fingers, first three fingers, F, B, I, like the agency, FBI. Take those three fingers. You've already got two of them perpendicular to each other. You just need to put the third one perpendicular to both of them. So it looks like this cool three-dimensional thing. So the force is middle finger, F, B, I. Okay? And you can orient this to solve problems, to figure out what direction is the force acting. Obviously, we're dealing in three-dimensional stuff here, so let's go ahead and quickly review. Into the paper, remember, is going to be the feathers on the arrow. Out of the paper is going to be the arrow tip. All right, so if we have a current-carrying wire placed inside a magnetic field, and the magnetic field will exert a force on the wire. So we have the current going through this gray wire. Current going in that direction. So this is going to be our thumb. What about the magnetic field? So we know it's got to come out of the positive and go into the negative, or out of the north and into the south. In this little well, it's doing the same thing. It's going out of the north and into the south. So our magnetic field is going to go to the left. So now we have our current going this way, and then we have our magnetic field going this way. What direction is our force? It's pointing up. So in this instance, F is going to be up. Orient your hand to try to match that. Do you see what's happening? You have the current going down the wire, so your thumb going down the wire. Remember, you're looking at this picture at an angle, too. So this magnet is at an angle, so the magnetic field is going to be coming from north to south, and then force pointing up. Force with the middle finger. For the other one, now we have current going this way, again through the wire. Again, our magnetic field is going north to south. So when we do that, we have current going here along the wire. We're going to point point the pointer finger along the magnetic field, and we get a force that is now going down. Can you match that? If not, ask for help. Out of the north into the south, out of the north into the south. So whenever you have this electric current pass through a magnetic field, you're going to get motion. You can create a motor to move like this. In fact, that's how they're made. Running current through a magnetic field, so you get motion. Something called a homopolar motor is very easy to make. You can YouTube it. See somebody using the right-hand rule over here. And basically it's just that. You have a wire connected to positive terminal of the battery while the negative terminal sits on a magnetic field. And what that does is it allows for the current to travel through, as long as your metal piece touches the magnet to complete the circuit to allow for the current to flow. And when that's happening, you get motion. So a motor converts energy from one form to another. As we just saw, electric motors convert electric energy or electricity to motion. This is not what a generator does. A generator, like the kind that you have in your house if the power goes out, or a generating power plant where electricity is generated and then transferred through the long wires to your home. Electric generators take motion and turn that motion into electricity. And this is done by rotating a magnetic field in a circular way, motion to electricity. All right, on to how a speaker works. A speaker works by having a wire wrapped around a magnet, so this coil that passes through electricity, going around and is connected to this cone. And as we've learned, when you have electricity passing through a magnetic field, you get motion. So what happens is the electricity is pushing upwards, that force that's causing this cone to go forward. And because the cone and the coil are attached, if you have current going in such a way that the force is pushing outward from your speaker, then the speaker goes out. The cone and the coil both go out. If you change the direction of the current, then the cone and the coil are going to go the opposite way. It comes back. And as it goes out and back at different frequencies, our ears receive that information as sound. That's what sound is, right? It's the vibration of the air particles. So if a speaker is going like this, then it's different sounds. This is how every speaker in the entire world works. Changing the current, changing the current's direction to sometimes push the speaker or the cone or the membrane out and then back in. So let's take a look at that. These little circles right here, let's say those circles, which normally are going to be labeled for you, those are going to be our current. So if the current is coming out, going through this magnetic field. Well, what direction is the magnetic field going? It's going from north to south. So we can use our right-hand rule, and if we have the current coming out, FBI, we have the current coming out, magnetic field to the left, the force is pointed down. Kind of had to turn my hand upside down to get that. So in this instance, our force is pointed down. Over here, if our current is in the opposite direction, then we have current going into the page, still have the magnetic field going from north to south. What direction is our force now? Now our force is up. Feels a lot more comfortable to have our force going up, at least when I orient my hands. So current going into the page, force going up, electric field going like that. Probably if I use my left hand, that would match up with the screen.